All right, good afternoon, everyone. Let's get started. So today we're coming back to our unit on model order selection. We started by considering polynomial models. And one of the neat things here is that we see that originally we developed these linear regression techniques. And what we see here is that they're actually quite powerful if you allow yourself to do some nonlinear pre-processing of your data before you apply that technique. So here, we have data that clearly doesn't fit well on a line. And so what we did was, instead of just using the raw data value x, we constructed new features, x squared, x cubed, all the way up to xd. And with that, we can do a much better fit, potentially. But the challenge we see in doing that is it's not really clear exactly which one of these, which of these new features to include, which not to include. And in particular, in this polynomial example, we have to figure out which polynomial order do we stop at? Do we just keep making our model more and more complex, or do we stop at some point? And that's really the main topic of this unit is figuring out how complex our model should be, what are the problems if it's too complex, if it's not complex enough, and so on. Okay, so that's sort of the setting. We're working on a synthetic data set that allows us to, since we know the ground truth, we know that in this case the true model order is 3. It's a cubic polynomial. That's useful to know. But you can see the data is quite noisy, and so it's certainly not obvious from the data itself what the best model order is. Okay, so what we did is we first said, let's imagine that a Gini tells us the true polynomial order d equals 3, and we fit our model. And we can see that in this case, we get a great fit. It's almost perfect. But then, because in reality we don't have that Gini to tell us what the true model order is, we considered other possibilities, like maybe we would have tried a linear model, in which case that's what we call underfitting, where the model is not following the inherent complexity of the data. The data is more complex than the model. The model is somehow, it's doing an okay job, but it's not doing as good as it could be. And then we have this case of overfitting, where our model is too complex for our data. And as a result, it's doing some sort of strange things. It's making some strange oscillations. And in this case, we also see that outside of the range between 1 and -1, which is where our training features lived, the model is going crazy. And so if we had test data that was outside that range, it would do absolutely terrible on that test data. And even within the range, like it would not do so well on test data that was around here. So these are just examples of what can happen when you underfit or overfit your model, when your model is too complex or not complex enough. And there's some other pictures here that I think show, these are just illustrations, but I think they do a good job of showing what can happen. And this is sort of an interesting one here, where you can see that in some cases it's possible for your model to actually perfectly fit your training data. It goes through all the training values perfectly, but then clearly if your test data is really following this sort of curve, it's not going to be exactly on this line, and so you're going to get errors. Another way you can think about what's going on here is that the model is fitting the randomness in the noise in the training data rather than the underlying structure of the features of the training data. Okay, so I think that's where we ended up last time. And so now we can talk more specifically about ways to figure out what the model order is from our data alone. So what about this simple idea? Basically, it's a two-step idea. We're going to consider, let's say, a range of hypothesized model orders, maybe starting at 1, and in this case, going all the way to 14. So we're going to consider 1, 2, 3, 4, and so on. For each one of those model orders, we're going to compute the least squares coefficients from our training data. And you can see that there's going to be d+1 coefficients. So every time we change our model order, we're actually changing the length of that vector. And then we compute the mean squared error on our training data. And here, by mean squared error, all I mean is that you're taking the RSS and you're dividing by the number of training samples to normalize it. In Spirit, it's essentially the same as RSS, it's just, you're just scaling it by a certain value. Sometimes people use MSE as a more interpretable version of RSS, but conceptually, there's really no difference here. Okay, so this is sort of, this is like a for loop. We consider different orders D, we fit the model, we evaluate the model on the training data, and in this case, we plot the resulting mean squared error. So you can see when the model order was 1, the mean squared error is high. When it was 2, it was high. Then it takes a big jump when it's 3. And remember, 3 is a correct model order, but we don't know that. And then, it sort of hangs out at a certain value, and then eventually it gets better and better. So what do you think? Is this going to be a good procedure for us to choose our model order from the data itself? Is this what we want to see?
So the one concern I have is, right, RSS was scaled based on like the variance size, right? So I'm kind of curious.
Oh, if we would, like you're saying, let's also divide this by, SYY.
That was kind of my initial.
We could do that. You would see that this curve would look identical. It would just be scaled, up or down depending on the value of SYY. So I would say that the particular scalings, whether we have the 1 over n there or not, is not really that important for us right now. It's more about the trend of the curve, the shape of the curve. So what do you think? Is this is just a simple idea. Is this a good idea or not a good idea? Does anybody have any thoughts?
I think that it would probably not be a good idea because
Okay.
it would overfit really hard. Like as you went up and you increased D, it would just it reduced the mean squared error by so much that it'd be overfitting.
Yeah, exactly. So, we see that from the curve, right? Like we see that as the hypothesized model order increases, this metric just gets better and better. It just gets lower and lower and lower. So if this is the way that it always works, then anytime we try this procedure, it's always going to choose the largest model order that we evaluate, right? It's just always going to tell us, use the most complex thing you can, right? And so maybe let's understand, is this actually always going to happen? And if so, why? So here's one way we can think about what's going on when we try different models as we just did. So when D equals 1, which is this case, we can think of our model, think of it in terms of beta. The beta vector is going to be beta 0, beta 1, right? Those are the coefficients we are allowing to adjust. And then you can basically think of it as all the rest of the betas, we're forcing them to be 0, right? Because we're saying this is a model order D equals 1, which involves those, and because it's D equals 1, there's no higher order coefficients. It's equivalent to us imagining that they're there and forcing them to 0. Everybody agree? Okay. Then, when D equals 2, it's sort of like we're using a beta vector that's beta 0, beta 1, beta 2, but then the others are forced to 0. And when D equals 3, it's like we have beta 0, beta 1, beta 2, beta 3, but then the higher ones are forced to 0, and so on and so on. Okay, so when you look at it this way, you can see that essentially, as I go from the first to the second model, I'm just allowing this 0 to be non-zero, right? I'm allowing it to have more flexibility, and here my least squares train procedure is the best possible thing we can do if we want to minimize training MSE or training RSS. So when I give it this extra freedom, it's only going to do better, right? That's what we saw when we compared simple to multiple linear regression. So when I allow this to be non-zero, if that helps me in minimizing training mean squared error, it will find a non-zero value and it will use that, and my training mean squared error will be less. And then when I go from here to here, if there's some beta 3 that should be non-zero, it will find that, and my training mean squared error will get lower as a result, and so on. And so like as I remove all these 0 constraints, my model gets more flexible, more capable, And I'm always training it optimally to minimize training MMSE. I'm using the approach that minimizes training MSE. There's no better approach. So according to this rule, things will only get better. Eventually they could hit 0 and stop, right? Once I fit my data perfectly, then I'm not going to fit it better than perfectly, but at that point we're in trouble because we're probably using a huge model order. So does this idea kind of make sense, thinking about it as like we have this nested set of models, we're just making our model more and more complex, that makes it more capable, we're training it in a way that actually does minimize training MSE or training RSS, and that's what's going to happen. It's only going to get better and better. Okay, any questions on this idea? Yes?
For example, do you find this optimal for training data? Then, I mean, we got the plane, the figure, the plot, the pattern that really matches the training data. But it can be, can't it be make a problem for test data?
Yes, exactly. That's exactly the issue. Is right now we're focusing on a metric, which, this is just what we chose to do. We chose to use this metric, and that metric is decreasing. We have the freedom to choose a different metric to be more clever, and maybe we get around this problem. So that's exactly right. Okay, so here's a case where you can see how it is that you can get perfect prediction. Mathematically, you could say, as you increase D, as you do that, your A matrix gets wider and wider because you keep adding a new column of data, right? As long as when you add that new column, those columns stay linearly independent, eventually you'll get a square matrix with linearly independent columns. It's invertible, and at that point, the optimal B's will just be A inverse Y. And then this will be 0, and you'll get 0. And this is an example of that happening. So, so this is the issue with this simple idea. It's a bad idea. It's not something we want to use, but we want to understand this and understand why it's bad. Okay, so is everybody with me on that? Bad idea because training MSE is going to decrease as I make my model more complex, or it's never going to increase, so that's not going to help us choose the model order. Okay, so now let's start to talk about things that will help us choose our model order. So the main idea behind all these approaches is we want to evaluate the performance on test data that is, let's say, different from the training data that we used in our model. So the simplest way to do this is just to take the data we have, n samples, and split it into two parts. Partition it into a training part and a testing part. We can use, let's say in this simple approach, we're just going to take ntrain, some number of the samples, and call them training samples. And we're going to take the rest of the samples, n minus ntrain, call that n test samples. We're going to use those for testing. And so this is how it's going to happen. Again, we're going to come up with a list of hypothesized model orders. In this case, let's say from 0 to 9. And for each one of those model orders, we're going to compute the least squares coefficients from the training data, as always. But then we're going to apply those to predict the test targets. And then we're going to compute our error based on the test targets. So training our beta parameters from the training data, but evaluating how well they work from the test data. Okay, so that's the approach. And when we look at the results, the green curve here is the test mean squared error. The blue is the training. As we expect, the blue curve is just decreasing. As we increase D, the blue curve just gets lower and lower. The green curve, initially it decreases, but eventually it starts to increase a bit. And so you can see it's not suffering from this problem of being monotonically decreasing. Okay. Now, did it work perfectly? No. If you look closely, the model order that you get from minimizing the green curve is 6. 6 is, we happen to know 3 is true. So it didn't find the right model order, but at least it didn't choose 9, which is what we would choose if we use the training MSE. And we see other kind of strange things. It's, sometimes it goes up and then down. And in fact, a key idea here is there's a lot of ways to partition our data. Like one thing you could try, I would say a naive thing, is to take the first N train samples as training, the last N test. The trouble with doing that is a lot of data sets come ordered somehow. Like maybe if you, it's impossible to know, but maybe the samples, the Y values are actually ordered from small to big. Okay, so if you did that, if you just took for your training set all the small Y values and tested on the big ones, obviously that wouldn't work, right? There'd be a big mismatch. So generally what you want to do is you want to randomize, you want to shuffle your data before you split it. Just randomly shuffle it and then split it. Now you can see that every time you come up with a different random shuffle, things are going to be a bit different. Your test and training sets will be different. And so these curves will look different. And that's what was done in the code, in the demo. So for this particular run, d equals 6 was the model order, but if I would run it again, I might get some other value. It might be perfect, it might be d equals 3. Who knows? It's going to be some value. And so that's another thing we would like to see if we can cut down on the inconsistency. So we'll propose a method to do that in a moment, but these are the sorts of things we see from this sort of simple idea, partitioning into two folds. So these subsets are called folds, partitioning into two folds, training on one, testing on the other. But that's kind of like, that's the big idea, is make sure you test on something different from what you trained on. Okay, any questions on this? Yeah.
Does this reduce the quality of the model because you're training it on less data?
That's a great point, yes. So we are using less training data, and we have this intuitive notion, we'll get more concrete about it, but we have this intuitive notion that we do better with more training data. So yes, we are compromising our training data by using less of it, and that's also an issue. And there's a weird trade-off here too, because if I say, well, I'm going to use most of my data as training and only a little bit as test, what's the problem with that?
You're not testing, guaranteed that you're testing it across the whole range, or
Yeah, so then my test metric is going to be inconsistent. It's going to be maybe wrong because it's maybe not representative of the trained data. So, so there's this real question about balance. And often people use like 80% training, 20% test. Sometimes people use 90% 10. Sometimes people use 50-50. There's no magic ratio there. It's all a trade-off. So here's an improvement. A more complicated but better approach, better in the sense of getting around to some of these issues that we just mentioned. This is called k-fold cross-validation. Okay, so it goes like this. As before, you shuffle your data set first, so you're pretty sure it's shuffled well. And then what you do is you split it into k different folds. So in this case, in this picture, we happen to have k equals 10. So this is just an example. And what you do is you actually train your model k different times. The first time you train it, use all of these folds together as your training data. You compute your beta vector on that, and then you use that to predict the labels in the test fold. And then you measure the mean squared error and you record it as the number you want. Then you start over again. You use all of these values as your training data, compute a new beta vector, use that to predict these test labels, and you compute the mean squared error of that. It's probably going to be a little different than the first time. And you do this k different times. Every time you're using a different fold for your test data. Eventually, you are using all of your test data, right, at least once, or all of your data as test data once. And every time you do it, you can see that here we're using 90% training and 10% test. So that's good. Maybe you could say this is a more robust training procedure. Okay, but now we actually have a bunch of different values of our test mean squared error. So the simplest thing to do is just average them and get an average test error. And repeat this procedure here for every hypothesized model order. So you're going to eventually get a curve like this versus model order, where each of those values is that average value here. And hopefully this is going to be more robust because you're using all your data for test, you're using all your data for train, you're using, every time you do it, you're using maybe more than, you're using at least 50% or more for training data and so on. So this is called k-fold cross-validation. As you can see, a lot of advantages. The disadvantage is it's expensive and it requires you to fit your model k times. So if your model is easy to train, doesn't take long, it's not a problem. But if your model takes, a day to fit, maybe this is the case for some neural networks, in fact, it could be much longer, then this could be really expensive. So you just have to use this where it makes sense. Typical values of k are 5 or 10. Okay. There's an extreme version of this where you use k equals the number of samples in the data set. So what that means is that the test fold always contains one sample and the training always contains the rest. So that's the most extreme you can go. It's going to be, in some sense, the most reliable, but in another sense, it's the most expensive because you have to fit your model n times. And so if your n, the number of training samples the number of total samples is small, it's not a problem. But if it's large, it's impossible to do this. Okay? But these are options for us in terms of how we're splitting into training and test. Okay. Any questions on the overall idea here? Is the procedure pretty clear? Yeah.
I guess I just want
Go
Oh,
ahead.
either.
double check. So every time we have to calculate our beta coefficients from the training data, right?
Yes.
So, and then we're having these hypotheses. So hypothesis of D equals.
There's like an outer loop over the hypothesis of D.
Okay.
And then for each D, you do all of this. So you can think of this as maybe an inner loop.
Okay.
So it's kind of like two nested loops.
Okay.
I'll show you the code in just a moment. Okay, is another question?
Yeah, maybe that's what you're gonna show next, just like which set of betas am I gonna choose? So I found out that it's order 3, so I'm gonna go and minimize it, whichever interaction or training data that I chose gave me the best result against the test.
So really the whole purpose of this procedure is to generate this green curve, a curve like that, so that you can choose the model order. Maybe I choose 4. Once I've chosen that, I can go back and I can retrain it with all my training data, all my data if I want. That'd be the smart thing to do. So really the whole purpose of this is not to train a good model, it's just to figure out the model order. Any other questions? Okay, so so here's an example. This is the nested for loop approach. And there's actually scikit-learn gives you much more automated approaches that we will see later. But first, just to understand how it's done, it's better to see a more manual version. So in this case, we're going to do the outer loop over k, the number of folds, for reasons that will be evident in a moment. And then the inner loop will be over the different model orders. And so essentially what we're doing in the innermost loop is we're computing the test MSE for each combination of model order and fold. And we're going to fill out this big matrix, right? One direction is model order, one direction is fold. Once we have that matrix all completed, we can average over the folds. Basically, we're doing this average, and that will give us a vector of model orders. Sorry, vector of MSE is 1 for each model order. That vector, when I plot it, gives me a curve like that. Okay, so I'm going to call that MSE bar D. The bar denotes sample mean because it's really just a sample mean of this. For every fixed value of D, I'm taking a sample mean across index K. Okay, so that's what we're doing. And then once we're all done and we have that curve, we're going to choose the D at the minimum point of the curve. Like over here, we're just looking for the minimum point of the curve, and the minimum might be 6 or whatever. Okay, so that's the goal, or the high-level procedure. Any questions on that? Okay, so let's look a little bit more detail about the code. So the most difficult part of this is coming up with the index sets that you use for training and for tests, because you need to use those index sets to extract the relevant samples from your code. And that's what scikit-learn gives you, this thing called a k-fold object that does that for you. So we're going to use this. This is in the scikit-learn model selection library k-fold. And what we're doing up top here is just instantiating this k-fold object. And all we need to do to tell it is the number of splits or folds we're going to use, which happens to be 10 in this case. And we're telling it shuffle the data. I can't remember if the default is to shuffle it or not, but it's always a good idea to shuffle it, because otherwise you can get into real trouble. Okay, we also have to tell it how many, what are the different model orders we're going to test. So in this case, it's going to go from 0 to 9. And we're going to initialize our matrix at zeros, and then we're going to fill that matrix. So the outer loop, again, is over the different folds, and the inner loop is over the model orders. And the reason we're doing it that way is because it's kind of a pain to extract our data for these different folds. And so this is the data extraction process. Once we have the data extracted, it's easy to fit many different model orders, which we're doing down below. Okay, so how do we do this data extraction? So this k-fold object has a split method, split function. You give it the x data. This is a matrix. It's really just at this point using the dimensions of that matrix to figure out what range of indices it needs to give you. And this is going to return something called ind. And ind is really two different vectors of indices. One is the training indices, the other contains the test indices. Okay, so every time you call this outer loop, it stores that value in there, and then here we unpack it into the training and test indices. And once we have that, it's relatively easy to take our total data, and for X data, you evaluated the training indices, and then you rename this XTR. That's all your training data for this iteration of the outer loop. Once we have all this stuff, it's pretty easy. We can use our polyfit method to do our least squares fit, our polyval method to evaluate our predicted training targets, and then we just use the mean command to get the mean squared error. For that particular I split, this is one counter, and then this is the iteration. This is the iteration counter for the model order. So this is just filling out one entry in that matrix. Yes?
Is default for the split method 80-20? Like, is that the percentage it's splitting into?
Oh, so you're kind of mixing two concepts. So the 80-20 idea only applies to this simple version. This is the simple just split into two.
Yeah.
What we're doing now is we're doing k-fold cross-validation.
Okay.
So k-fold is parameterized by k, the number of folds. We're using 10 in that example. And so you could say implicitly when you do that, it's always going to be 9 out of 10 folds, 90% for training, 10% test.
Gotcha.
And if I would have used 5, k equals 5, it would have been like, 4 folds for training, 1 for test, so 80-20.
Okay.
So it's really controlled by k.
Gotcha.
Yeah.
What would indicate, like in that sample, what would indicate that the dimensionality that you're testing for is like too low? Like if it's actually like 11 or 12?
Oh, okay. So the whole purpose of all this code is just to get this, it's basically to get this matrix here. And then once we have the matrix, we average across our folds to get this vector here. And then we need to find this lowest point. That would give us our model order estimate. And now the question is, how do you evaluate that? At least here we know the truth is 3, so that can be how we tell. But it's a good question in practice. In some sense, this is our evaluation of it. That's kind of, because if no one tells us the truth, the best we can do is evaluate it on an independent test set and see how well it does there.
If it if it turns out that it's like 10, like in that example, and you're only testing up to 10, should you then increase and try it again?
So, yeah, good question. So if you see that it's sort of maxing out, it might be that the grid you chose for hypotheses wasn't wide enough. Maybe you need to look at larger values. Another thing you could do is run it again, because this whole process is random because of the shuffling. Every time you run this, you're going to get different results. So run it a few times. See, is it always on that edge? Is it always 10? That's a good indication that, yeah, 10 isn't big enough. But maybe the next time you run it, it's going to be 2, and then, okay, it just happened to be 10 that one time.
So is the shuffling the primary reason why the leave one out cross-validation might be more accurate in some data sets?
Well, more accurate than the simple method?
Yeah.
I mean, so the simple method is kind of like what you would do is you would just split it. Simple method is kind of like doing this once and stopping there.
Yeah, sorry, I'm not wording that correctly. Since you're taking a portion of it, the leave one out cross-validation, since you're always taking like one sample, you're not really shuffling that much.
Are you're asking about, sorry, about that one?
Yeah.
Yeah. So that one, so I guess you could maybe look at this from several ways. So one way is like you're using almost all your data every time for training. So maybe it's good in that sense. You're going to have a huge number of these guys to average when you're done. It's good in that sense. You could say maybe it's not good and that maybe there's a little average here that's going to be small. So it's not exactly obvious, what is the best K. And so that's why people that have actually tried to study that, they say it's usually 5 or 10 is a good balance between all this stuff. But one interesting thing is if you do this, it's deterministic. It's no matter how you shuffle it, you're going to get the same result every time. In fact, you don't even need to shuffle it, right? Because you're kind of looking at every possible combination of leaving one out. So shuffling the data doesn't change anything.
Yeah, that was the main question.
Okay,
Is it,
yeah.
like always consistently.
It will always be the same, right? But anytime K is less than N, the shuffling will affect the result. Okay. Okay, so good. So this, yeah. So if you try this stuff, you'll see that this K-fold cross-validation, yes, it does work better than that simple method, which is sort of just like doing this once. It really does help to look at different test folds to average and all that stuff. All right. Any last questions about the method? Okay. So now we're not done because as you can imagine, we already said here that every time you run this, you get a different result. So that tells you that the things we're computing here are not perfect, right? They're not optimal. They vary. So we have to be careful how much we trust them. We don't want to trust these values as they're varying a lot. We can't say, this is exactly the true mean squared error. We don't know because every time we run it, it's different. So we need to have a method to figure out how much do we trust the data. So one way to think about this is, can we put confidence intervals on the results we get from K-fold cross-validation? And just before I get into the details, it's kind of like this. So this underlying curve is what we've been constructing, but what I'm doing differently now is notice I'm putting these confidence intervals on every point. And you can see that for some model orders like 0, I'm not really confident on the value that I'm getting, whereas for these ones, I'm much more confident. This is probably the most confident. So that's what these things are telling us is how much to trust this value. It's kind of like you're saying, okay, the code returned this value, but the truth could actually be anywhere in this range. I shouldn't think that this is exactly the true value. Right. So that's the goal, is to put confidence intervals on things. And the main way to do this is to use something called the standard error. So the definition for standard error is going to be the standard deviation of our mean squared error for hypothesis D divided by the square root of k, which is the number of folds, or remember, this MSED is like a vector of length k. It has k different values. So in other words, this is the picture we've seen. This is like the MSED. It's a vector of different MSEs. Here, I'm looking at the mean of it. But I might also be interested to know how much do these guys vary from this mean? Are they all very close to the mean, or are they varying wildly from the mean? Right? Because if they're varying wildly from their mean, what does that tell you about the mean? It's not that trustworthy, right? If these guys are like all different from the mean by a significant amount, then should we trust that mean? Probably not. But if they're all very close to the mean, you feel more confident about, yeah, that's actually probably true. It's always turning out that way. Okay. So, all right, so this is a nice way to get that confidence. So you take that vector of values, you compute the sample standard deviation. That's what's done here. And let's just take a quick look at this. So we have a square root, right? So really what's in here is the sample variance. And that's the same equation we've seen before, except we're using this unbiased version. In units 1 and 2, we didn't have this -1 there. So now we're seeing that -1. What that's doing is it's making this multiplier a little bit larger than if it was just 1 over k. And the smaller k is, the bigger this -1 has an effect, right? So, so this is more important as k gets small. And when you're doing cross-validation with k equals 5, 5 is a pretty small number. You're only averaging 5 things. That's not a very robust average. And so that's why it helps to try to get the unbiased version of the variance. Okay, so so that's, we're going to learn, we're going to come up with, we'll see exactly where this equation comes from very soon. But for now, it's just a way to get confidence bounds, or yeah, this works for any average. It's not specific to mean squared error. Oops. Works for any average of k numbers. Okay, so it's like, imagine that you want to know how much someone makes in a profession, and you get a list of salaries of people in that profession, and you want to know, and you average them, and okay, you get a number like 100K. So you want to know, is that accurate? Well, if all the salaries are very close to 100K, the standard deviation that you're computing here would be very small, and your standard error would be small, and be like, yeah, that's pretty accurate. But if you saw some people are making 50K, some people are making 150K, that 100K is just kind of a rough number, right? You could definitely apply this to salaries. It applies to any time, any quantity you're averaging. It's not specific to MSE. We just happen to be using it for MSE in this application. Yeah.
Does it make sense to plot like 2 sigma or 3 sigma bounds like we do in other error practices? Don't we get like more confident at a tighter bound?
You can imagine that. I mean, I think it's enough just to have this rough idea. This is just kind of telling us which ones are more reliable, less reliable. And yeah, of course, like if you imagine having larger sigmas, then it goes larger. But yeah, we're not going to do that. We are going to use these values in just a moment, but right now it's just understanding what is this standard error. Is it pretty clear now how we're going to compute it and what it's doing for us? Okay. So one thing about the computation is, so the way that okay, let's look at the code. So evaluating the mean in Python is very straightforward, right? We have this np.mean command. So we have now a matrix. So we have to tell it whether to look over the columns or the rows when it computes the mean. And that's what this axis command is doing. Would be axis 0 would be do the mean across each column. Axis 1 would be do the mean across each row. So it's doing the mean across each row of the matrix. But what about the standard deviation? That's np.std. So here's how we get it to use this -1. We put it in this DDOF argument. Okay, so the code says DDOF equals 1. That means it's going to subtract 1 from k. If for some reason I wanted to subtract 2 from k, I would put DDOF equals 2. Or if I wanted to subtract nothing, I could put a 0 here. But that's what this DDOF does. It just subtracts some number from k when it evaluates this whole thing. Okay? And then the last thing, the square root k is easy. That's just right here. To get this nice plot with the error bars, that's called plt.errorbar. You just got to give it the vector of the solid things, and you give it a vector of the one-sided standard errors, and it plots them using those little vertical lines. Okay, so this unbiased thing, this is important. This is important when k is small. If k was big, it wouldn't really have much of an effect at all. Okay, so the next thing we can talk about is we can actually use these error bars in a clever way. And it's something called the one standard error rule. This is just a heuristic rule. There's nothing optimal about it, but it tends to work pretty well in practice. The idea is based on something you may have heard of called Occam's razor. Is basically when there's multiple explanations that are valid, choose the simplest one. That's the guiding principle. So the way it uses that is it says, use the simplest model giving an MSE bar within one standard error of the minimum MSE bar. Okay, so let's look at the chart here. It shows us. So the minimum MSE bar, to figure out that, we look at the solid line, and we look at the lowest that it gets. In this case, it happens to be at 8. It's hard to see here, but if you ran np.min, you would find it. This happens to be the lowest point. So this is going to be we're going to call that d-min. Okay, so now it's saying, look at one standard error of the minimum value. So that would be, the mean square error at the minimum value is the solid line. The top of its error bar is one standard error above, right? So this dashed orange line is this thing, MSE bar target. MSE bar target. That's the orange line. It's a line that's at the top of the error bar of the lowest point in the curve. So Occam's razor says, okay, any one of the model orders giving the solid line below the dashed line, they're all equally good explanations of a good model order to choose. They're all kind of incorrect. Especially this one is incorrect. We don't trust it. We only trust it up to a certain limit, and these guys are all within that limit. So they're all good enough. Let's just choose the simplest one. Because we're choosing a model order, as we go to the left, the models get simpler. And so of all these, the simplest one that is, that we can trust is basically 3, which happens to be the truth. It's not always going to work out to be the truth, but in this case it did. And as you can see, it's helping us navigate between all these almost equally good solutions and just focusing on the simplest one that's pretty good. And so this is what we would call D1 standard error. This is what we get out of this method. So again, it goes like this. First step, choose dmin as the minimizer of MSE bar, the solid line. Second, set MSE bar target at the top of its error bar. So it's MSE bar dmin plus standard error at dmin. That's the orange line. Last step, find the smallest d such that MSE bar d is less than or equal to MSE bar target. So that took us from d min equals 8 to d equals 3 in this example. So it really helps to cut down on the sort of variability that you see. Like if you would run this again, next time, probably not going to be 8, it might be 6, it might be 4, but you would see that one standard error d, maybe it's not always 3, but it's, often 3. Okay, so this is a pretty good technique to use to get our model order fit. All right, so is the procedure clear enough? Any questions on step-by-step procedure? Are you good with this? Okay.
Professor,
Yes.
are we normally gonna find once, like in the minimizer, like in the minimum of the MSC, small standard deviation? I'm asking that because if it's large enough, it could take me to the second order.
Yeah. Then we would have reason to believe that maybe it's the second order. Yeah. It's, I don't know. It's,
Okay, any data set can do this.
yeah. This is the method. It's a heuristic. It's not always going to be optimal, but it, usually works better than just choosing the minimum value. But it certainly can go wrong. Yeah. As your data set gets smaller, all of this gets harder, gets more noisy. It's just not going to work as well. So, all right. Any other questions? Okay. All right. So we have some decent methods now of doing our model order fit. But let's step back and talk a little bit about training and test data again, because as some of you may know, there's kind of another data set that people talk about in some situations. So we're going to talk about this in terms of training, test, and validation data. Now, training data, it's pretty well understood what that means if you look at different papers and books. But people interchange the meanings of test and validation. There's no consistent use of these terms. So sometimes when someone says test, it's what someone else means by validation and so on. But let me try to explain what these three different things are. So the training data, we refer to the training data as that which we use to train the model, and maybe, let me be more specific, I'll say the model parameters. And for example, in this case, it would be our beta vector. Now, the test data is the data we're going to use to tune the model hyperparameters. So the hyperparameters are parameters which are not directly using like a large, training data set to train using minimizing training RSS and all that. It's stuff like model order D that we need to select that actually changes our whole model. And we need to use data to select it, but it's not like we're running, it's not like we're doing a least squares fit to get D. We're using some maybe more complicated procedure. The key idea is that both of these we're using during the design process. Out of both of these comes finally a model and a parameter vector. Now, the validation data is something that you use after you're all done designing to test how well this worked. And you're not supposed to go back based on that and redo your model. Because at that point, that new data set is actually being used to design your model, and you really can't call it validation data. So validation data is like something that you strictly hold out. You never touch it until you're really all done. And when you're all done designing, then you can say, how well did this actually work? Okay. Otherwise, if you're going back, you're really using that as test data. It's not really validation data. Okay, so one example where you'll see this is in a machine learning contest, like this contest on Kaggle, where they really want to be fair. You know, a lot of contestants putting in effort. So the people who run the contest, they have some validation data that only they know about. And they hold this secret, and at least part of it is only released once the contest is over. And at that point, they test all the models on that data set and they see who won. Okay, they don't allow people to go back and redo their model. It's not fair. Okay, so that's really one place where you'll see this validation data. Yeah, so hopefully it's kind of clear. The first two are used to design your method. Some is used to train your parameters. As we know now, it's really important to split this into training and test, to do, for example, model order selection with the test. And then once you're all done, then you can evaluate how well that all worked on the validation data. Okay, so when you look through papers and books, you'll often see those terms swapped. Some people will say validation data is what you use for tuning your hyperparameters, and the test data is what you save to the end. Okay, it's not, there's no agreement. It's like 50-50. So it's just good to know that those terms can be interchanged. So just if you're reading something or you're writing something, make sure to be clear on what the meaning really is. We're going to try to be consistent through this course to use those three terms in those ways. And in this unit, we're not even considering validation data. I'm just bringing it up because it's a good time to bring it up. We will see this validation data in the project at the end of the term. There will be a Kaggle, in-class Kaggle competition, and there will be data that's held out until the end. But just wanted you to be aware of these three different types of data in case you run into this terminology. All right, any questions on anything here? Yeah.
For validation data, could it be something where you have the feature data but you don't have the targets, or do you just not have access to it at all?
Yeah, so the way Kaggle does it is that way. So they give you the features, but they don't give you the targets. Now, sometimes if you're clever, you can still gather some information from the features in a way that can help you. Like sometimes people will actually they'll do some prediction of what they think the targets are, and then they'll try to figure out which of those they're more confident about the validation targets, and then they'll actually pretend that they're correct, and then they'll use them for training. And that's fine. You're allowed to do, with the given data, you're allowed to do whatever you want to do, and that can actually help if you do it well. But that's exactly right. In Kaggle, they give you all the features, but they only tell you about the targets for a portion of the data. And in that case, it's up to you to split it into training and test. Or, when you do K-fold, you're doing this splitting, but in many different ways simultaneously. So, all right. Okay, any other questions about this stuff? Okay, great. So that pretty much brings us to the next topic, which is going to be one of the most important lectures of the semester. We're going to try to describe these ideas with a bit more mathematics. We're going to get into some random variables, expected values, things like that. So this will recall some of the prerequisite on basic probability. Let me just go forward. So I'm going to talk about things a bit in class, but probably you won't be able to digest all this stuff if it's really rusty. There is a little thing that I wrote, which is similar to that linear algebra handout. This is a similarly length handout on probability and expectation, just the stuff we need for this course. So if you want to take a peek at that, beforehand, you're welcome to. It's there on the GitHub repo. It's just trying to go through just the basic stuff that we need for this course. So you don't have to feel like you need to read a whole textbook. So with that, I'll see you guys on Wednesday.